In this film we're going to go through the part of the physics GCSE specification on nuclear equations, and it would be useful for this film if you got yourself a periodic table to look at. I'd suggest if you've not got one, pause the film now, find your periodic table and get yourself set up. Right, the first thing to look at is actually take a look at this periodic table and just remind ourselves what the numbers on each box represents. So let's go for iron, just as an example. And we've got iron we can represent like this. So we've got the symbol, we've got a number at the bottom here, and we've got a number at the top here. And there's iron on the periodic table. We need to know what these different numbers represent, and this is useful for chemistry and for physics. So this bottom number is what we call the proton number, or the atomic number. And is, as the name suggests, it tells us how many protons there are in iron. So in iron we know there are 56 protons. This top number here tells us the relative atomic mass. So that's the relative atomic mass, and that's the number of protons plus the number of neutrons. So here we can make a note: protons plus neutrons. So we already know that iron has 26 protons. So if the relative atomic mass is 56, then 26 of those are protons. That must leave us 30 of those to be neutrons. So iron here, 26 protons, and we said 30 neutrons. 56, take away 26, leaves us with the 30 neutrons. Okay. Now when we come to do nuclear equations, we represent alpha and beta in in similar ways. So let's pick a colour and let's stick with this. Let's stick with this green for alpha. And alpha, if you remember, is like a helium nucleus. So alpha we can write with the symbol He for helium. And then we remember if it's like a helium nucleus, well, a helium nucleus has 2 protons and it has 2 neutrons. So 2 neutrons plus 2 protons leaves us 4 up there. So that's how we can represent alpha. Sometimes it can also be represented like this, with the symbol alpha, but the numbers will be the same. So both of these are alpha. So we might see alpha represented in either way. Beta, let's go for colour for beta. Let's go with this orange. Beta, draw a box. Remember, beta is a fast-moving electron, so we can use the symbol E. And as it's an electron, it's got no protons and no neutrons, so we can put a 0 here. Now, the strange thing here is thinking, well, it hasn't got any protons, but it's got the opposite charge to a proton. So rather than putting a +1 there, or a 1 there, because an electron's got the opposite charge to a proton, we represent it with a -1 there. And again, like we did for alpha, beta we could also represent with a beta symbol, like this. So there's beta. Both ways of presenting beta, both ways of presenting alpha. Now, there are some certain decays that happen naturally. And by decay, we mean if we've got an element, and let's start with uranium. So we'll go with uranium-235. What might happen to uranium is that it might give off an alpha particle. And this is a fairly common decay. So if it gives off this alpha particle, let's represent it like this. All we need to do now is think about, well, what's left? So this uranium started off with 92 protons. 2 of them are thrown out with the alpha particle. 92 minus 2 leaves us with 90 left here. It started with a mass of 235. 4 of them were given off. That leaves us 231. So we're not quite sure what the element is yet, but we know that uranium has given off this much helium and has changed. It's got a different atomic number. The atomic number, remember that's our number at the bottom, is different now. So this is where we go to our periodic table. So we're looking at our periodic table and we're looking for, well, here's uranium, but we're now looking for something with the atomic number of 90, and it's here, thorium, TH. Now you might notice that the number at the top on your periodic table for thorium, if I bring this a little bit closer, number at the top for thorium is 232. Yeah, we've written 231. Well, the main thing, guys, is to always go with this number at the bottom. That tells us what the element is, and then stick with what you've calculated. And what we've discovered here is that this is an isotope of thorium. So this is an isotope. And you might remember what an isotope is. An isotope is a similar, or the same element, except the number of neutrons is different. So the proton number is the same, but the neutron number is different. I'd like to write it like this: same protons, so same number of protons, but different number of neutrons. And if we compare the one we've found on our periodic table, 232 and 90, compared to 231 and 90, we can see this one must have one less neutron than the one on our periodic table. So same number of protons, still 90 at the bottom, it must have a different number of neutrons. Okay. That's all we do for an alpha decay though. We start with our element, we're told it's given off some alpha, and we work out what's left. And once we've worked out what's left, we use this number at the bottom, go to our periodic table, and find out what element it is. Let's try it again with another example. So this time, let's go with radon. Sorry, not radon. We'll go with radium. So on our periodic table, radium has an atomic number of 88, and this radium we're going to go with 226. And not to confuse you, but just so you realise it could go in any order, we're going to put our alpha here. We might only be given this in the exam, in assessment. Okay, so we have to remember, so our number at the bottom for alpha is 4, at the top is 2, and now we're working out what's left here. So 88 minus 2, 86 at the bottom, 226, and then 4 have been given out with this alpha particle, 222. So we go to our periodic table, we're looking for 86, it's the bottom number we go with. Let's have a look at our periodic table. Well, radium was here, but we've got to go down to 86, which is radon, Rn. So radium becomes radon. And I'm going to do one more now, but I'm going to suggest that you pause the film and see if you can work this one out yourself. So this is why you'll need your own periodic table. We'll go with plutonium. Plutonium-238, and it has got an atomic number of 94. So I'm using an isotope of plutonium here. And all I'm going to tell you is it gives off alpha. And I'd like you to pause the film and have a go at completing it, working out what's left. And then once you've done, unpause the film. Okay, hopefully you've had a go at that. So let's go with our numbers we know for alpha. We need to learn these 4 and 2. Let's look at what's left then. So 94, 2 protons given off, leaves us 92. The mass was 238. It's reduced by 4, 2, 3, 4. Bottom number we're going to use to find out what it's become on our periodic table. And our plutonium has become uranium. That's got the 92 at the bottom. So I need to put in the symbol for uranium. Well done if you work that out. Again, it's an isotope of uranium. But the key thing is, we use the number here that we've calculated, we use the number here we've calculated, and we use this bottom number to find out what's left. Right, let's do the same again, but for some beta decays. So beta also has some elements that decay, that will give off beta, but they follow a slightly different rules, as you can see, because the numbers here are different for beta. So let's go with an isotope of carbon. Carbon is always carbon. If it's got the atomic number 6, that's going to be carbon. But this time, rather than being carbon 12 that you'd see on your periodic table, we're going to use an isotope, carbon 14. And it's going to decay by giving off some beta, giving off a beta particle. So let's go beta, 0, minus 1. And let's work out what's left. Now, beta I think is a little bit fiddlier, a little bit trickier to get your head around than the alpha decay. Top number is easy. Look, 14, take away 0, leaves us 14 at the top still. 6, take away minus 1, 6 subtract minus 1 gives us 7. I guess we can check this by 7 plus minus 1 is 6. That balances. A bit like we did on the other side, we can check 90 plus 2 is 92. So with beta, this number actually goes up by 1. So you can either remember that by always remember that beta, the proton number goes up by 1, or just applying your maths. 7 plus minus 1 gives us 6. Do it on your calculator if you can't remember or if you're not happy with that. So now we use that bottom number, remember, just like we did for the alpha. We find out what has 7 at the bottom, and it's nitrogen. So if carbon 14, we would call it, decays by giving off some beta, it actually becomes nitrogen. So what's really happening here? What's really happening? Well, during a beta decay, an electron is emitted from the nucleus. And you might say, but there aren't electrons in the nucleus. And you'd be right, because actually what's going on here is, let's have a look, we've got 1 extra proton now, yet this number at the top is still 14, this is still 14. So to start with, we had 6 protons, 8 neutrons, that makes it 14. Now we've got 7 protons, must only have 7 neutrons. So what's actually happening is a neutron has turned into a proton, and in the process, it also emits an electron, or produces an electron. So a neutron turns into a proton and then emits an electron, and that electron is the beta decay. And we can think about this with our charges. So we can remember the charge on a neutron is 0. Neutron has no charge. The charge on a proton is +1. And if we left it as that, the equation, we'd go from no charge to positive charge. But like all things in science, things need to balance both sides of an equation. So to make this balance, we have to have something with negative charge, +1 plus -1 gives us 0. Now we're balanced with the other side. So that's the process that's going on there, and there's some of the maths behind it as well. So let's do another beta decay. Do another beta decay, and we'll go with potassium. So potassium, atomic number of 19, and we're going to go with an isotope here. So potassium 40, going to give off some beta, and we're going to think what's left. Top number, 40 minus 0, easy, stays as 40. 19 minus 1 means it goes up by 1, so we're looking for something with that atomic number of 20. Remember, so is that bottom number? Let's just put a box around this, keep this out of the way. Always that bottom number. Where is the 40? Sorry, 20 is a bottom number. Where is the 20? Calcium. Calcium. So we're using that bottom number, calcium. Okay, so this time our potassium has given off a beta, and it's become potassium. So one more example for you to try, and again we'll pause it for a bit. I suggest you pause it, and then you can carry on. So let's go with plutonium again. So this time we're going to go with plutonium 241. Plutonium, and it's got the atomic number of 94. And I'd like you to complete that for a beta decay. So pause the film, unpause when you're done. Right, hopefully you had a go at that. Let's put in our beta. So it's given off a beta particle, that fast moving electron. Top number, 241 minus 0, stays as 241, that bit's easy. 94 minus 1, that becomes 95. Grab our periodic table, something with the atomic number 95, americium. AM. Okay. And finally, a mention for gamma. So is our other radiation is gamma. Well, gamma is the Greek symbol for gamma. You remember it's got no mass because it's a wave, and it's got no charge. So if we were to give it a box, that gamma would have 0, 0. And that means that anything that does give off gamma, well, there'd be no change to the top number, no change to the bottom number. So we don't really do nuclear decay equations for gamma. Hopefully that's been useful. There you go.